China's largest radio telescope just handed scientists 2 years of continuous data on one of the most mysterious signals in the universe. James Webb followed up on the exact same signal from space. And together, they just answered a question that astronomy has been failing to answer for decades. If that sounds like the kind of thing that should be front-page news everywhere, subscribe right now and stay until the end, because the full picture of what these two telescopes found together is genuinely one of the most extraordinary things to happen in astronomy in years. Let's start with what a fast radio burst actually is, because without understanding that, none of what follows makes sense. A fast radio burst is a flash of radio waves from deep space. It lasts for a fraction of a second. In that tiny sliver of time, it releases more energy than the sun releases in several days. Sometimes in 3 entire days' worth of solar output, compressed into a few milliseconds. Then it's gone. No warning, no explanation. No obvious source visible in the sky afterward. The first fast radio burst ever recorded was discovered in 2007 when Australian astronomer Duncan Lorimer was going through archived telescope data and found a signal that had been recorded in 2001, but nobody had noticed. A flash of radio energy from somewhere far outside our galaxy, lasting 4 milliseconds, carrying enough energy to power civilization for centuries, and completely unexplained. That discovery opened one of the deepest puzzles in modern astrophysics. What in the universe is producing these things? What object? What event? What mechanism could generate that much energy in that little time and then just go silent? For 17 years after Lorimer's discovery, astronomers were working almost blind. They could detect fast radio bursts, they could measure how much energy they carried, and the numbers were staggering. A single burst in a few milliseconds releases more energy than the sun produces in days. They could calculate how far they had traveled using a clever technique involving the way different radio frequencies get spread out as they pass through the plasma between galaxies, the same way white light gets split into a rainbow when it passes through a prism. The more spread out the signal is, the further it has traveled, because it has passed through more plasma. Using this technique, astronomers established that fast radio bursts were coming from other galaxies, sometimes billions of light years away. That distance made the energy calculations even more astonishing. If a signal that faint has traveled billions of light years and still has enough energy to register on a radio telescope on Earth, the amount of energy at the source must have been absolutely enormous, but they could almost never figure out exactly where in the sky a burst came from, which meant they could almost never identify what galaxy it came from, let alone what object inside that galaxy was generating it. Without knowing the source, all the theories in the world were just guesses. Scientists proposed magnetars, which are neutron stars with extraordinarily powerful magnetic fields left behind after massive stars explode as supernovae. They proposed collisions between neutron stars, events that also produce gravitational waves. They proposed exotic objects called quark stars, cosmic string vibrations, and other hypothetical phenomena. Nobody could prove anything because nobody could pinpoint where the signals were coming from with enough precision to identify the actual source object. That frustration defined the first decade of fast radio burst research, a phenomenon powerful enough to be detected across billions of light years of space, and no one could say for certain what was producing it. Then 2 things happened that changed the situation completely. The first was the construction and operation of China's 500-meter aperture spherical radio telescope, known as FAST, or the China Sky Eye. Built into a natural depression in the mountains of Guizhou province in southwestern China, FAST is the single largest and most sensitive radio telescope ever constructed by human beings. Its dish is 500 meters across, roughly the size of 30 football fields placed side by side. To put that scale in perspective, the previous record holder was the Arecibo Observatory in Puerto Rico, which had a dish 305 meters across and was considered the greatest radio telescope on Earth for over 50 years until it collapsed in 2020. FAST's dish is roughly 60% larger than Arecibo's was. It sits in a landscape that looks like something from a science fiction film. A vast bowl of almost 4,500 triangular aluminum panels nestled between hills that were specifically selected to shield the instrument from radio interference generated by human technology. The panels are individually adjustable. The overall parabolic shape they form can be changed in real time to focus on different regions of sky as the Earth rotates. The 19-beam receiver at the heart of the instrument can simultaneously observe multiple nearby regions of sky, dramatically increasing the efficiency of surveys. The construction of FAST required relocating nearly 10,000 residents of the surrounding villages so that their electrical equipment would not interfere with the telescope's observations. The Chinese government funded the entire project, which cost approximately 1.2 billion yuan, or roughly $180 million at the time of completion. Construction took 5 years. The telescope entered full scientific operation in January 2020. When it did, it was operating with a sensitivity that no other radio telescope in the world could match. If a fast radio burst is faint, too faint for other telescopes to detect clearly, FAST can see it. If a signal is repeating, but the individual bursts are weak and brief, FAST can track it over long periods and build up a detailed picture of how the signal evolves over time. It was exactly the tool that the fast radio burst problem had been waiting for, and almost immediately after it went into full operation, it began producing results that other instruments simply could not have generated. The second thing that happened was the James Webb Space Telescope. Launched in December 2021 and beginning full science operations in 2022, Webb is the most powerful infrared space telescope ever built. Its mirror is 6.5 meters across. It sits nearly 1 million miles from Earth at a point in space called L2, where it can observe the universe without the infrared glow of Earth's atmosphere interfering with its measurements. Webb was primarily designed to look at ancient galaxies, the first stars, exoplanet atmospheres, and the deep structure of the universe. But its infrared sensitivity also made it uniquely capable of something no previous telescope could do: follow up on a precisely located fast radio burst and look for the faint infrared glow of whatever object had produced it. By themselves, each of these two instruments was extraordinary. Together, they produced something that astronomers described as a turning point in the field. And the story of how these two telescopes connected, one on the ground in China and one floating in space 1 million miles from Earth, unfolds across two separate but deeply linked discoveries that happened within months of each other in 2025 and 2026. The first discovery came from FAST. Starting in June 2022, a team of researchers, led by scientists from the Purple Mountain Observatory of the Chinese Academy of Sciences and the University of Science and Technology of China, pointed FAST at a specific repeating fast radio burst source called FRB 222529. This source had been discovered by CHIME, the Canadian Radio Telescope, and had been confirmed to repeat, meaning it was not a one-time event, but a source that kept sending out bursts at irregular intervals. The team used FAST to monitor it continuously, not a few observations spread over a few weeks. A continuous monitoring campaign that ran for nearly 2 years, from June 2022 all the way through August 2024, accumulating 125 separate observation sessions and more than 58 hours of on-source telescope time pointed directly at this single object in the sky. What they were measuring was a parameter called the Faraday rotation measure. This is a number that tells scientists about the magnetic field and the density of plasma in the environment immediately surrounding the source of a radio burst. When radio waves travel through magnetized plasma, the plane of their polarization rotates. The amount of rotation depends on the strength of the magnetic field and the density of the electrons the waves pass through. By measuring how this rotation measure changed over time as FRB 2022-4529 continued to produce bursts, scientists could learn something about the environment around whatever object was generating those bursts, even though they could not directly see that object at the enormous distance of 2.9 billion light-years away. For the first 18 months of FAST's monitoring campaign, the rotation measure of FRB 220529 showed only modest, relatively stable fluctuations. The magnetic environment around the source seemed roughly constant. Then, in December 2023, something extraordinary happened. The rotation measure suddenly surged to roughly 20 times its average variability. 20 times. Then, over the course of about 2 weeks, it dropped back down to its normal range and stayed there. A dramatic spike in the magnetic environment of the source, appearing suddenly and then disappearing just as suddenly. This is what made the binary system connection unmistakable. If the fast radio burst was coming from an isolated neutron star, a single object sitting alone in space with no companion, there was no known mechanism that could explain a sudden spike in the rotation measure that large, appearing over days and then disappearing over 2 weeks. Isolated magnetars don't do that, but a neutron star in a binary system orbiting alongside a companion star would experience exactly that kind of change. As the neutron star's orbit carries it close to its companion, the plasma and magnetic field expelled by the companion star would suddenly be in the path of the radio waves traveling outward from the neutron star. The rotation measure would spike as the waves passed through that denser, more strongly magnetized environment. Then, as the orbit continues and the neutron star moves further from the companion, the rotation measure would drop back to its baseline value. The pattern is a signature, and what FAST recorded in 2 years of patient monitoring of FRB 2022-0529 was precisely that signature. The results were published in the journal Science on January 15, 2026, the most prestigious scientific publication venue in the world. This was the first time in the history of fast radio burst research that anyone had directly captured the evolutionary process of a burst source, watching it change over time in a way that reveals the nature of its environment. It was the first real, direct observational evidence that at least some fast radio bursts come from binary star systems, rather than isolated objects. Duncan Lorimer, the same physicist who had discovered the very first fast radio burst in 2007, commented directly on the fast result. He called it a remarkable result and said it was a testament to the power of the fast radio telescope in China to make these monitoring observations. Professor Bing Zhang of the University of Hong Kong, a corresponding author on the science paper, noted that the finding supports a broader theoretical model in which all repeating fast radio bursts may originate from magnetars, but magnetars whose behavior is shaped and modulated by the presence of a companion star in a binary orbit. Now here is where James Webb enters the story in a way that makes the two discoveries inseparable. 1 month before the fast binary discovery was published in Science, something happened on the other side of the world. On March 16, 2025, an array of radio telescopes called CIMA and its new network of outrigger stations spread across North America detected the brightest fast radio burst ever recorded. The burst was given the scientific designation FRB 2025-316A and a nickname RBF float. And it briefly outshone every other radio source in its entire host galaxy. It lasted a fraction of a second. The energy it released in that fraction of a second was enormous. And because the CHIME outrigger network was operating, this burst was localized with a precision that had never been achieved before in real time, pinpointed to a specific location within a specific spiral arm of a galaxy called NGC 4141, located 130 million light-years from Earth. 130 million light-years. Close by cosmological standards. Close enough that the best telescopes on Earth and in orbit could potentially follow up on it. The team immediately contacted the James Webb Space Telescope team. This was the first time since Webb began operations that scientists had been able to pinpoint the location of a fast radio burst precisely enough to aim Webb at the exact spot within a galaxy where the burst had originated. Webb turned its infrared eye on that precise location inside NGC 4141 and found something. A faint source of infrared light, very close to where the radio burst had occurred, given the designation NIR1. Peter Blanchard, a postdoctoral fellow at Harvard and the lead author of the JWST follow-up paper, described the moment directly. This was a unique opportunity to quickly turn JWST's powerful infrared eye on the location of an FRB for the first time, he said, and they were rewarded with an exciting result. The faint infrared source NIR1 could be a red giant star near the end of its life. It could be a massive middle-aged star. Either way, it is the kind of star that could be the companion in a binary system that also contains a neutron star or magnetar producing the radio bursts. Or, alternatively, the infrared glow could be a light echo from a powerful flare event that produced the burst itself. The results were published in the Astrophysical Journal Letters in August 2025. What makes the combination of these two discoveries so significant is not just what each one found individually, it is what they confirmed together. FAST watched a repeating fast radio burst for 2 years and found the magnetic signature of a binary companion star changing the environment around the source as it orbited. Webb looked at a different fast radio burst in a nearby galaxy and found what appears to be a stellar object sitting right at the location of the burst. One instrument proved the binary connection through radio monitoring. The other instrument showed a potential visual counterpart through infrared imaging. Two completely different telescopes, two completely different technologies, two completely different approaches, converging on the same answer to the same question. Fast radio bursts, or at least some of them, come from magnetars in binary star systems, objects so exotic that they do not exist anywhere near our solar system, spinning dense remnants of dead stars with magnetic fields trillions of times stronger than Earth's, orbiting companion stars, and periodically producing flashes of radio energy so powerful that they can be detected across billions of light-years of space. Now consider what China's contribution to this understanding has been. FAST has been the indispensable instrument for the most detailed, long baseline monitoring work on fast radio bursts that exists anywhere in the world. Its sensitivity is unmatched. Its ability to detect faint bursts that other telescopes would miss entirely is what made the FRB 2022-0529 monitoring campaign possible. FRB 2022-0529 is intrinsically faint, meaning its individual bursts are too weak to be easily detected by most radio telescopes. Most facilities would have been able to catch only the brightest bursts from this source, if any at all. Only FAST could watch it continuously, session after session, over nearly 2 years, and build the data record comprehensive enough to reveal the rotation measure spike in December 2023. That spike, that 20-fold surge in the magnetic environment signature, followed by a 2-week return to baseline, is the piece of evidence that proves the binary connection. Without FAST sensitivity, it would never have been detected. Without the patience of continuous monitoring that FAST enabled, the pattern would never have been identified. The binary discovery, published in Science in January 2026, was made possible specifically because China built an instrument sensitive enough and was willing to commit enough telescope time to do science that no other country's telescope could do in the same way. And the international team that published the result included scientists from China, Hong Kong, Australia, the United States, and multiple other countries, all working together with data collected by a Chinese instrument sitting in a mountain valley in Guizhou province. What is also significant about FAST's operation is how broadly its data is being used. The telescope has identified more new pulsars, rotating neutron stars that emit regular radio pulses, than any other instrument in history. It has detected the gravitational wave background signal through pulsar timing. It has mapped the structure of hydrogen gas clouds in the Milky Way at a level of detail that was previously impossible. It has studied magnetars, the extreme magnetic objects that are now strongly implicated in fast radio burst production, in its own galaxy and in others. Every time FAST looks at the sky, it is generating data that the international scientific community uses, analyzes, publishes on, and builds new theories from. The results are not kept private. They are published in journals like Science, Nature, and the Astrophysical Journal, the same high-quality, peer-reviewed venues where the most important astronomical discoveries in the world are announced. What FAST is doing is open science on the highest level, using an instrument that happens to be owned and operated by China. The data from FAST is not hidden or secret. It is being published in peer-reviewed journals and shared with the international scientific community. But FAST's role in fast radio burst research has not received the attention it deserves outside specialist circles, partly because the instrument itself is so far from major English language media centers, and partly because fast radio bursts are a deeply technical topic that most science journalists find difficult to translate for general audiences. What happened when FAST's 2-year monitoring campaign and Webb's first ever fast radio burst follow-up observation came together in the span of a few months is a story that deserves to be told loudly and clearly. Two of the most powerful astronomical instruments ever built, one Chinese and one jointly American, European, and Canadian, looked at the same phenomenon from different angles and with different technologies, and arrived at the same answer together. And there is more coming. China's space telescope, called Zhuntian, or the Chinese Space Station Telescope, is scheduled to launch in 2027 aboard a Long March 5B rocket from the Wenchang launch site. It will operate in low Earth orbit at an altitude of 400 kilometers, flying information with China's Tiangong space station and able to dock with it for servicing and instrument upgrades. Its main mirror is 2 meters across, slightly smaller than Hubble's 2.4 meter primary, but its survey capability is dramatically larger. Its field of view is roughly 300 times wider than Hubble's, meaning it can map enormous areas of sky in a single pointing while maintaining a resolution of 0.15 arc seconds, essentially as sharp as Hubble. It carries a suite of instruments including a survey camera, an integral field spectrograph, a multi-channel imager, and a terahertz detection module. When it is operational, its sky survey data will identify thousands of potential fast radio burst host galaxies across vast areas, providing targets for follow-up with FAST on the ground and with Webb in space. The picture that emerges when you look at what FAST has already done, what Webb has just begun to do with precisely localized fast radio bursts, and what Zhuntian will soon add to the combination, is of an astronomical capability that has never existed before. A ground-based radio telescope with the sensitivity to track faint repeating sources for years at a time. A space-based infrared telescope with the resolution to find individual stars at the locations of those sources in nearby galaxies, and a space-based survey telescope capable of mapping the sky deeply enough to ensure that the locations of thousands of future bursts can be identified and followed up immediately. All three instruments pointed in different ways and with different technologies at the same fundamental question. What is out there at cosmological distances that can produce flashes of energy powerful enough to be detected across billions of light years of space? The answer that FAST's 2 years of data and Webb's first ever fast radio burst infrared follow-up are pointing toward is specific, testable, and genuinely exciting. At least some of these bursts come from magnetars in binary star systems, dense, extraordinarily magnetic remnants of dead stars, orbiting companion stars, periodically producing radio flashes so powerful that the universe delivers them to our telescopes across billions of light years. The companion star shapes the magnetar's radio environment as it orbits, producing the changing magnetic signatures that FAST's 2-year dataset captured in 2023. The companion star, or the light echo of the burst itself, may be the infrared source that Webb spotted at the location of the brightest burst ever recorded, 130 million light years away. Both instruments and both discoveries are pointing at the same physical picture. The question of what produces fast radio bursts was unanswered in 2007 when Lorimer found that archive signal. It remained unanswered through most of the 2010s as detection rates improved and more bursts were cataloged. By 2020, CHIME was detecting hundreds of new bursts every year, and the catalog was growing faster than theories could keep up with it. Some bursts repeated. Some appeared only once and never returned. Some came from nearby galaxies a few 100 million light years away. Some came from sources billions of light years in the distance, from a time when the universe was much younger than it is today. In August 2025, a team using the Meerkat telescope in South Africa published a paper announcing the detection of a fast radio burst originating 3 billion years after the Big Bang, one of the most distant ever found, with James Webb identifying the faint, clumpy host galaxy at the location of the source. The universe was producing these events when it was young. It is producing them today. Whatever is generating them has existed throughout the history of the cosmos. It remained unanswered when CHIME began detecting hundreds of them per year. And now, in January and August of 2025 and 2026, FAST and Webb together have delivered the clearest answer yet. Not the final answer. Science does not work that way. Future observations will test this model, challenge it, refine it, and possibly overturn parts of it. But the convergence of two instruments, one built in a mountain valley in China and one floating in space a million miles from Earth, on the same answer to the same question, is one of the most compelling developments in observational astronomy in years. Subscribe. If real science told clearly and accurately is what you are here for, share this with anyone who underestimates how much the rest of the world is contributing to our understanding of the universe, and comment below with what you think the next big fast radio burst discovery will be. The FAST data archive is enormous and still being analyzed. Researchers around the world are combing through it, looking for patterns, for repeating sources, for new rotation measure anomalies that might reveal other binary systems hiding inside the data that was already collected years ago. Webb has dedicated time allocated to fast radio burst follow-up observations in its upcoming schedules, and every newly localized burst that lands in a nearby galaxy is a new opportunity to find the infrared companion object that finally shows us what these systems look like. And Zuntian is on its way. The discoveries are not finished. They are only getting started.